Hi, my name is Dustin Thompson.
And I'm John Holliday.
And this is our fluids project.
For our fluids project, we chose to verify the Bernoulli's equation. In order to do so, we used a manometer.
But hey John, this is a groundbreaking theory. We can't just use any manometer, can we?
I don't think so.
So that's why we had to personally design what we like to call the ultimate manometer.
We placed our manometer in front of a water hose with a free-flowing stream and held it there until we reached equilibrium height.
And we measured that height, and then in order to use Bernoulli's, we had to pick 3 different points in our system. Our first point is the center of the end of the water hose, which is, we're actually going to be calculating the velocity there using Bernoulli. Our second point is the center of the entrance of the manometer, and our third point is the free surface inside the manometer. So, using a ruler, we calculated the height in our manometer, which came out to be about 0.175 meters. From this height, we did a Bernoulli equation from points 2 to point 3 in our system. So here's our equation, and you know the elevation at point 2 we chose to be 0, so that cancels. And then you know that the pressure at point 3 in our system is 0 because it's an open surface, which means there's atmospheric pressure. And elevation at point 3 is going to be our measured height. So the only unknown we have left in our system, our equation, is the pressure at point 2. So we calculated the pressure at point 2, which came out to be about 1,717 pascals. Once we found that pressure, we wrote down another Bernoulli equation, but this time going from point 1 to point 2. So in our equation, the pressure at point 1 can cancel. You know it goes to 0 because it's a free-flowing stream, so the pressure is 0. Our elevations at point 1 and point 2 cancel because they're equal to each other. And then you know that the velocity at point 2 is 0 because the velocity at the entrance of the manometer is 0. So that leaves the velocity at point 1 in our system and the pressure at point 2 is the only things left. And we know the pressure at point 2 because we just calculated it. So solving for our velocity, we're able to get that the velocity coming out of our end of our water hose is approximately 1.85 meters per second. But this number cannot stand alone. In order to test it, we had to use quantitative measurements to see if we could get the same results.
For our measured quantities, we used a 3.5 gallon bucket and calculated the average time it took to fill that bucket over 3 trials. We took our control volume and divided it by our average time to get the discharge of the flow rate. From there, we calculated the velocity at the end of the water hose by dividing the discharge by the area, and we come up with 1.86 meters per second.
So as you can see, our quantitative measurement was 1.86 and our theoretical measurement was 1.85 meters per second of the velocity coming out of the water hose. These numbers that we came up with are within a 10% error of each other, so you can properly conclude that the Bernoulli equation stands and holds true, and that you can use it to find various pressure and velocity distributions throughout a real-life system.